This covers some concepts in chapter 1. Um, so I also have a video already made that you've probably seen about data versus information. So this is kind of a review of that. But this is just an introduction to what databases are and why you have them, and we'll focus more on databases in general, and then we'll get into some more detail about designing databases in the next segment, I guess you would call it. So we've already gone over this data, dodari dedidatum, the principal parts in Latin and all that stuff has to do with the word give. So it's just a little bit of repetition here. A datum is a given. So data are givens, so they're just facts, bare facts that you have that you need to store, and then you get information from that data by using databases. If you want to just put it in a nutshell, databases are a structured way of storing data. There's all kinds of different styles of databases, and that's the main thing I want to go over in this video, is just talking about the different ways databases have been constructed, and sort of where we're at now, and maybe like a preview of the next steps. So some good resources. These are some notes I think I made on reading when I had my last class. I'd already taught databases. I'd had a class already on databases, but then for school red tape reasons, I thought it'd be an easy class. It was a little harder than I thought actually in the end, but it's a grad school class on data. The one thing you might not know about computer programmers and computer science is that this stuff has to do with computer science for sure, but database stuff has kind of been a side issue, more like library science than computer science. When you talk about a curriculum in general for computer science, it would be, in the past, it would have been very easy to have never had a class on databases in a computer science class. Got to keep in mind, computer science versus computer programming, there's a little bit of difference there. Computer science is more like the mathematics of computability, as opposed to just like learning programming. So there's a difference there, and databases are more on that utilitarian side. But the theory behind creating databases is definitely a computer science topic, but it's not one that's like central. So it's recently you'll see in computer science curricula that study of databases is coming more and more into the center. But anyway, that's a big tangent. So that's kind of why, yeah. So I decided. So these are some notes I did on the reading and defining some terms. So like knowing these terms would be good. This one, I don't think you see this one come up much in class data catalog. You'll see it more in the form of metadata, and I'll go over that here in a second. So database, again, it's just a structured way of collecting data, and there could be all kinds of databases. So I'm going to skip down. It might not actually be in this document in my reading, because I don't think I covered this stuff in this document. So let me see if I can find. Here we go. This is just a random website I googled because I know which terms I want to demonstrate, and I wanted to look for good pictures to show you. So this is After Academy, whatever this is. But the ones I want to focus on are these right here. There are, of course, a lot of other ones, and we won't cover. Actually, we probably won't cover many of these right here. There's another kind of database called NoSQL, and some variations on that we'll talk about a little bit. But I just want to briefly go over these because they have pictures and I like that. So hierarchical model. There could be different ways of doing this. The most common, I don't want to say common, but if you go back a few decades, the most common way you would experience a hierarchical model would be like I think I mentioned this before, file cabinets. File cabinets, you could have several different file cabinets, right? And then inside each file cabinet, you have several drawers. And then in each drawer, you would have several folders. Maybe you have like dividers between sets of folders. And then in each folder, you'll have maybe several documents. That's a hierarchical model. So imagine that you have a shoe store. They'll put that at the top. And then you have two file cabinets, a women's shoes file cabinet and a men's shoes file cabinet. And then you have two drawers there. And then in each drawer, you have several folders of different kinds of high heels and maybe like documents on that. So this is like, I'm trying to make it work with this picture, but for you guys, like if you ever in this, you guys are almost all probably too young for this, but I'm not. Card catalog at the library, that's hierarchical. So you'll have different, the hierarchy is the alphabet usually, I think, or call numbers. I'm trying to remember how they all worked actually. Is it call numbers? I think it was the alphabet, because you would look it up under title or maybe author, maybe it was mixed in there, and then each card, there would be a drawer for each one, then there'd be a whole bunch of cards, and you would look through the cards for the right author and or title maybe. I can't even remember if maybe they were divided up in author and title. And then you would find the card for the book you want. It would have like the location in the library and other information about it. And it's been so long I can't even remember how it works. But that's kind of a hierarchical model. Your file system on your computer is a hierarchical model. So you have a root folder. Usually they're called partitions. They can be physical or logical or like kind of both at the same time. So your C drive is a logical partition. That's the root of the hierarchy. And then you have subfolders in that, and then each one of those folders can have a subfolder. So that's hierarchical. And we got some features here. I don't want to go over this in detail because I don't want to like get too deep in the woods on this, but some of the things you just notice about it is that in order to have women's shoes, you have to have shoes, right? You have a root somewhere, and then if you deleted the women's shoes node here in this graph, this is called a graph, by the way. This is a tree. This is a tree graph, acyclic graph. A lot of this stuff has to do with graph theory. I won't get too deep into that. But if you delete this node, these nodes are gone. So the parent node, if you delete it, the children node are gone. All the children nodes below that. And if they had children too, they would be gone. So if you threw out a drawer in your file cabinet, all the folders in those drawers would be gone, right? So that's one of the problems. Maybe you could call it a problem with a hierarchical model. One of the restrictions, I guess. So then the next con is network, and I don't really like this picture. I should have found it more complicated, but network you have, and if you notice, you got arrows here for both of these. This goes from here to here, right? If you think about the order, you'd have to look for things in. There's an arrow, you go in that direction. This is network models are the same, except these arrows can go in any direction, and they can go back and forth. You don't really see that here, but the library can point to the college too if it wants to in a network model, and that's a little bit more flexible. What else do I want to say about it? So some of the problems you might have with the former model, for one thing, you notice you have one-to-many. So this thing has many children, and each one of these can have many children, right? But it doesn't go the other way, because you don't go the other way at all, actually. But for this college could point to both of these things, and this library can point to the CSE department if it wants to. There's no reason it can't. The logic might dictate otherwise. If you look and see how this thing that this modeling is set up, this department, it looks like, it might not make sense for this to point to that, but it could. That's my point. It's like, depending on the design, these arrows can point to anything in a network model. So, and there are, I focused on file cabinets with these, but there are computer versions of hierarchical models. Like, for instance, your file system is kind of one, and there are other, I've never used consciously. I wasn't aware if I was using a hierarchical electronic database. That's just like a general database, general purpose database, but they exist. They are older, usually. I guess, I'm trying to think. There may be some, like if you had electronic early card catalog, actually, it could have been done in, it would be electronic, it would have been hierarchical. And I've never consciously used a network electronic database either, but they do exist as well. All right. So the one that's most often you're going to encounter is this one, and I want to combine these two, because you see how they're two different ones here. They're actually the same thing in a way, like mathematically, and I'll explain what I mean by that here in a second. But you got the entity relationship model. You're going to learn how to make these before the end of the semester. So this is sometimes called an ERD or ER diagram. So there's all kinds of different words for it, but this is a diagram of what you will eventually convert into a relational model that you put into a relational database. So the next database really is a relational database. And the way you would see this ER model, entity relationship model, will be in preparation for making a relational database, because it's kind of a one-to-one thing. Not almost. I'll explain how it's not at some point, but you can kind of think of this as a predecessor of the next. All right, so in this model, you have things called entities and you have things called relationships between the entities. So entities are like your nouns, and in your whatever thing you're modeling, say like in this case you're modeling a school looks like, and this is just the teacher part of it. So this teacher works in or works for a certain department, and this department has probably more than one teacher in it, and we'll talk about that. You'll learn about that soon enough, about the numbers between these two things. And then each one of these entities can have attributes, so traits about each individual entity. So a certain teacher will have a certain name, a certain ID, like either in the database, it's just for purposes of the database you have a unique ID, or maybe the school issues an ID so that they can look up by the ID who the teacher is, or really both purposes at the same time is what you'll typically have. Like it's like your P number as a student at Pellissippi. And then, teacher makes a certain salary, has a phone number, has an age. Now, I hate when these things come up because this is like a side example. It has nothing to do with the lecture right now, but an age should be what's called a derived value, which means instead of storing the age in the database, you store the date of birth, and then you just say, hey, what time is it right now? Do the math. That's how old the person is. But we'll talk more about those kinds of things later. But the key thing is here is you have these things called entities, and they have these attributes around them. That corresponds to the relation. So this thing right here, this teacher and this department, this will be a table in your database in a relational model, and this will be a table, because what you'll have, and I wish they'd use the same example of the teacher here, but imagine this is teacher ID, teacher name, salary, that's one of the things, mobile, all that kind of stuff. You see how that kind of converts, that if this were the teacher or employee was in the other model, whichever way you do it, see how this converts directly to a table. So all these things up here, if you take this plus this plus this plus this plus this, all these attributes together into one thing called a tuple. They have that word here somewhere. A tuple is just a combination of values. If you take all those things together, you're describing something called a relation. A relation corresponds to entity. Again, entity relationship model, that's the rectangles. These are entities. These correspond to relations in a relational model. The teacher would be a relation, department would be a relation, and then those eventually will be in a database, a relational database. Those will be tables. And this is what a table would look like if you printed out the values in it. So again, this is the relation. Imp ID, this thing, the column headings combined together define what's called a relation. And then when you take a relation, a model with relations, and input them into a relational database management system, you'll get the result is a table. There's tuples. Each row in the table is called a tuple. So yeah, this plus, well, each row, I want to say the column headings in my mind are more what the tuple is. Actually not. The values are the tuples, that's right. If you take all these values together, they define a tuple, but those tuples correspond to these attributes that you would have in a relation. So attribute or field. So I should probably put this, maybe I'll put a link up to this. I don't know if I need to make sure all the stuff in here is correct on top of what I'm saying. But so those are the main ones. The last one's object oriented. Don't worry about it too much. Just know that it exists. It corresponds to object oriented design in object oriented languages like Java. And I'm going to assume most of you either don't have like a lot of history in programming, just like officially school wise. Maybe personally you do because you've done it on your own or whatever, done it somewhere else. But at this point in the curriculum, you should not have probably completed at least a computer programming class. But both the main ones that we teach, well, all the ones we teach, let me think. Python's object-oriented, C++ is, and Java is super object-oriented, C#'s object-oriented. So that's not necessarily saying that that's the best way to make a programming language. It's a big debate, actually, but it's the most common one family of one way of describing programming languages is object oriented, and it's very common now. But those objects that you have in object-oriented programming languages correspond to like ways of organizing the data too. So you have an employee object instead of a relation. And a lot of the stuff that you have in a relational model does kind of map down to objects, but objects can also do things. That's where this method comes in, like get hired or complete task or whatever for an employee. Don't worry too much about the object-oriented model, though. I will say it's still not the most common. It does have its uses, especially if you're doing databases for some kind of project that involves object-oriented language. That sometimes it makes things easier, but to me, this is the most common. Relational databases are what you're going to see most often. So they're the ones you want to get the most familiar with, along with maybe the NoSQL. I would even put that above object-oriented for sure. I haven't ever used object-oriented database that I know of, unless there's, let's say, I bet some of the main ones you can incorporate those features in, sort of. But in any case, focus on the relational model and understand the rest of these, the hierarchical and the network, mainly as like historical, like this is like an evolution. So you had hierarchical, and then network made some things better. One of the things you have in a network database model that you don't have in a relational database model is something called a many-to-many relationship. I kind of talked about this before, but like a library could relate to many instances of a college, and a college could relate to many instances of a library in a network database. In a relational database, not necessarily the ER diagram. The ER diagram can do many-to-many relationships. Like, imagine a teacher can be in more than one department, and a department obviously will have more than one teacher usually, right? This like all the English teachers, right? And then maybe you have a teacher that's in English and also math. That's a many-to-many relationship. You can directly model that here. It's not visible, but there's some easy changes you can make to this additions to show that. When you have relational databases like MySQL or Oracle or all the ones that we'll access, the ones we're learning about, you can only have one-to-many relationships and directly. You can have many-to-many relationships, but they have to be modeled in a different way that we'll learn about later. It's one of my things I like to talk about the most, actually, how that's done. But you can't directly do many-to-many relationships in a relational model. It's all broken down into one-to-many. It's one way of thinking about it. So one-to-many would be, for instance, if this employee, if there's another table, it might be like company. One company employs many employees, and one employee is an employee of that one company. That's not a great example. Maybe you could have departments for this too. So each employee works for only one. Oh, here it is, department ID. Department 2 can have many employees. You notice there's 2 right here, right? This employee is in department 2, and this one is 2. But each one of these employees will only have one department. That's a one-to-many relationship. All right, so that kind of goes over a lot of the most common database structures. Now, there's a lot more than that, but those are the main ones, and those are the ones I want you to focus on, maybe review. After watching this video, go back and say, okay, let me read more about the hierarchical model and that kind of thing. You don't have to know super details about them, but you need to know kind of where, the whole point of this is, where does the relational model fit in the whole history and evolution of databases. And again, these other models are still out there and here and there. I wish I should have prepared to have some like names of like maybe ones you've heard of or I've heard of those kind. But when it comes to relational models, again, that's the focus of this whole semester. If you wanted to like pick one database design, what's the word I want for it? Paradigm that we're going to focus on is relational. And that's MS SQL Server. That's like the main Oracle databases. That's MySQL. That's Access. And there's probably like some you've heard of and I've heard of. I'm not thinking of right now, but those are the main ones. All right. So still going over some of this basic info. So metadata data is the actual fact you stored. Metadata is data about the data. So you can keep going meta forever, right? But for an example, I like this example. A quantity for a product, you can't have half a product in your database. Like it's broken in two. That's just one you would throw out, right? So like these are things you think about like when you're like describing the data in a database. So the metadata for the quantity would be that it's an integer from 0 to some upper limit. So one thing you'll find out working with computers is there's always a limit because computers are finite machines. Mathematical theory, you can have infinity, but you can't have infinity in real life. You can sort of try to, you'll have more than you ever will use, so it's effectively infinite in your mind, but it's not really. But anyway, an integer is a whole number. You don't have point in it, or you don't have 1/2. It's not one. You don't have 1/2 or 0.25 or anything like this. It's just 1, 2, 3, 4, 5, 6, or 0, or the negative numbers. Negative 323. That's a negative whole number, right? That's a negative integer. We're saying like the metadata for this particular in this database catalog, and again, you probably won't see that term catalog too much, but the metadata, the data beyond the data, meta means beyond, right? Is that we decide. This is one of the rules. When I need to talk about that too. One of the rules that we're saying here is that we can't have negative products. Now, in real life, I think you will often see like for what you call it, stock, for like a store or whatever, you might have negative values for quantity. And what does that mean? It usually means shrinkage. I think it's the term for it, right? Theft or loss. You don't know where it went, and you're supposed to have. I don't know. It does come up. Does that come up negative? Actually, I guess it could be. I don't know. There's ways you can have negative quantities though, but we're saying for this particular rule, for this particular database that we have in theory as an example here, we're saying that you have 0 or more. So you either have no product, or you have 1 or 2 or 3 or 4. So that's metadata. Another metadata would be like a name has to be alphabetic characters, right? A through Z. That would be metadata. The fact that it has to be alphabetic is metadata. Zip is 5 digits or 9 digits, depending on how many you want to do, right? If you want to do the zip plus 4 or whatever. That's the fact that it's 5 numerals from 0 through 9 that fact is metadata. So that's what we mean when we're talking about metadata. All right, so other things you need to, like these terms, again, you might not see exactly these terms, but you'll see something corresponding to them. So like end user, that's the person who, I like the word quotidian. That means daily, right? I could have just said daily access. Daily access to a database is the end user. And then you might, like there's some other ones, and these are things probably you could find people defining these differently or chopping them up into different categories differently. But there's one user, I don't have it right here, but there's a kind of user that's not as like the boss. He doesn't use the database every day, but here it is. Here's these different types of end users. So you got the casual one. So he doesn't access the database access it frequently himself, but when he does, it might be weird stuff, like exceptional stuff that you don't do every day. The regular person doesn't do every day. So that's the naive or parametric end users. So these are specialized terms. You don't need to know these terms. But it's good to know kind of the idea about, well, because why are you using databases? This is showing you some of the tasks, right? This boss is like, hey, how many things did we sell in this weird location, this zip code? It just comes up for some reason. He might want to know that. The front desk worker at a hotel, he's going to be doing the same stuff over and over again. Which rooms are open? How do I assign this guest to these are going to be things, the same thing all the time, every day. Oh yeah, and then and if you're working in science, you might have to know a bit more about. You might not even have to work with the database directly, but you have to know what the database experts can do with the database to help you, like crunch your numbers or whatever. Personal data, like this is your stamp collection or whatever. I don't know what stamp do people do that. Oh, so my puppy. I did one for my puppy. I had we got surprised with a. This is a big tangent, but I won't go to. But we rescued a dog, and we found out she had puppies. She sprung them on us, so I kept track of the daily weights of the puppies on a little web page. And what kind of database was this? It was an ad hoc. It wasn't even really a database, was it? I was just graphing the weights over time, so it was kind of a flat file. That's another kind where you just have you just kind of throw the numbers on. You don't even worry. I guess you could say it might have been a spreadsheet, so it was kind of a relation, but not in a sophisticated, formal way. All right, so some other things you need to know about databases just in general. I just want to hit the high points. Maybe I'll try to cut this down to 30 minutes before I go to chapter 2. You need to be able to, you have to know what the scale of your database is. And I think I talked about this a little bit, but is it just like personal use, like the one I was talking about with my puppies? Or is it like a small dental office? I talked about this, I think, already in a video when I was doing the access stuff and guiding you through that exercise. You might not have got to it yet if you're watching this video first. I don't know which order you're going to watch them in, but so it might be a small mom and pop shop. Mom and pop still sounds wrong when I say it. It might be a huge enterprise where you have thousands or hundreds or thousands of end users doing queries on the database to get information all day long. Like every few seconds or every second, there's somebody else doing a new query, and in all kinds of different ways. That's enterprise level. That's multi-user. So one of the things you have to be concerned about with that level is transaction concurrencies, what it's called. So if you're changing the same record as somebody else roughly the same time or almost exactly the same time, you have to have some way of figuring out the logic of who goes first, what changes first, that kind of thing. So there's some transactional logic that database management systems have to do. This is a basic term that I didn't. The database management system is a mechanism, usually software. So almost all the time when we say DBMS, we're talking about a software program that manages databases. So I already told you some examples of these. I might have called it database, and people use these interchangeably, database management system versus database. When I say MS SQL Server, Oracle, Access, these are database management systems. The databases are actually just the data collected in a structured way. A database of all the books you own, a database of all the products that this store has, or a database that handles the products and the customers and all those things. That's that one purpose kind of collection of data for a certain purpose. That in a structured way is a database. A database management system is software usually, and I guess you could call file cabinets a database management system also. But like the electronic software ones, they manage one or more databases. I know the last job that I had with databases, where I worked with databases, we had many different databases in that database management system. A lot of them kind of looked the same, honestly. They were for different clients, basically. BMW and who else? That's just one example. Cricket was one of the clients, the phone people. So you'd have a different database for each one sometimes. A lot of the tables look the same though, honestly, in that case. But they were all running in Microsoft SQL Server. So that's the database management system. And it looks like this probably will go over 30 minutes because we're 1 minute away. So other things that you want to, DBA, a database administrator. That is the person who will usually run a DBMS for a company or something. He's kind of an IT guy, but he specializes in the stuff that we're talking about now, but he really knows it and runs it. He's the boss of the database, basically. Sometimes you have a specialized role for that in your business. Sometimes it's like the programmer has to do double duty as DBA. We're the place I'm talking about where I worked. All of us on the team, we're mini DBAs. We had to also set up the database as far as setting up the tables and each database, right? And then the tables in and the relations between them and what the table looks like, and backup schedules and putting them online for the user management, all that kind of stuff. Triggers, if we have views, whatever. We had to do all of those tasks as well as program the front end and stuff. So that's why it's a good thing to learn a little bit about databases, because you might be thrown that job at some point where you it depends on the scale of the company. It's not always the hardest job. You can sometimes manage it along with your primary software duties. And even if you're not the DBA, you sometimes need to do like mini tasks underneath, like more menial tasks instead of the like really important ones the DBA does, but they're still DBA-like tasks. So again, DBA, database administrator. It's a common name for a job type that you would have in this world. Okay, I think that's enough. And there's a lot of like other stuff here that you don't have to necessarily, you can like read over the doc. Maybe I'll put this up for you guys to look at, but you can like kind of review it. Some of it's more future stuff that you haven't got to yet. And I think that's it, except for, yes, one other thing. One of the concerns about database when we're talking about these different models, they all have different issues. There's certain things that can come, that they're pros and cons, I guess that's what I want to try to get at. So one of the things that you'll come into, and I wish I had a good example of this, I'll just put this in general terms right now. There's always, this is one thing you have with databases, there's always this strife, conflict, something you have to resolve. I'm trying to think of the word for it. There's a synonym for that word. There's a conflict, there's a strife, there's a contention, whatever, between two big principles. There's performance, how quickly you can get the data, how quickly you can operate on it, how much time does it take to do all the tasks you need to do with your data, versus consistency. Consistency just means, or integrity is another word for it, accuracy, correctness. So all these different models like hierarchical network, relational, object-oriented, and so on have pros and cons in those two areas. I think networks more quick, it's more efficient. It's quicker than hierarchical. I think it might even be quicker than relational. Relational is usually pretty slow because you have to like find the start, right, and then the child, and then like if you were thinking about the file cabinets and the folders, you'd have to find the right file cabinet and then the right drawer, and then you have to find the right folder inside of that drawer, and you hope that there's some kind of organization of that, so it's like alphabetical or chronological or whatever. That can take a while. So there's speed of access to the data versus consistency. So this is a big thing, and one of the related integrity and consistency issues to that is something called data redundancy, and that's where you have a piece of data, a datum, like a certain fact about something, stored in many places inside of your database, and that's only because of the way your database is organized. The structure of it can happen. So I'll just give you a real quick example. If you had a spreadsheet, just say you did database by spreadsheet at your little doctor's clinic, and you just have like a spreadsheet of all the patients, and then each patient, there will be a column in there somewhere who the doctor that patient has is. So Dr. Smith, Dr. Brown, etc., etc., and then you need to know the doctor's phone number. So patient 1 has Dr. Smith, whose phone number is 555. Patient 2 has Dr. Smith, whose phone number is 555. So like you've got all these columns in your spreadsheet. I wish I should have the actual spreadsheet. And I actually thought about doing this and I didn't do it. But Dr. Brown, the third patient has Dr. Brown, whose phone number is 222. Or whatever. Of course, this is not a real phone number, but I don't want to think up 7 digits. What if Dr. Brown changes his phone number? What that means is that he has to you have to go into that patient spreadsheet for maybe 1,000 patients, and let's say a third of them have Dr. Smith. You have to go to the phone number for Dr. Smith and all those 300 something, 333 and a third patients, and change the phone number in each of those locations. That's data redundancy. You can design a database to where the phone number for a certain doctor is stored in only one location. And then when it changes, this is called the update anomaly, what I was just talking about. When it changes, you change it in one place. So you know it's been changed everywhere it can be changed, which is the one place. There are database structures, and you might say, well, nobody's going to do that, but they do. You'll look. There are database structures. For example, in the hierarchical model, you might have like the same document and copies, right, in different folders. And then if you change like a piece of data, like the address or somebody on one, or say a lady got married, we still change names so far, but or both of them get their names hyphenated or whatever. You would have to go and find all those records that have that and change it in all those places. Ideally, the name will be stored in one place, and then when it's updated, it will be updated in one place. Otherwise, update anomaly, what can happen is it gets updated in one of the locations where it's stored and not the others. Same thing with a deletion anomaly. Let me make sure I get this one right. These are all from the top of my head, but deletion anomaly would be, let's say you somehow magically deleted all of Dr. Smith's patients just because each one of those patients decided to leave. Maybe maybe he cussed out each one of them every time they visited him, and like everybody left. So in your database, you delete the patients that leave the clinic, right? If you delete all those patients, you've lost his phone number. Now, obviously, you can imagine like, okay, what's your phone number, right? And you write on a piece of paper. But in the database, if deletion anomaly would be if you delete all the records that some other record depends on that thing being there in several locations. If you delete them all, you lose information you don't want to lose. That's deletion anomaly. Insertion anomaly is when you insert something more than once, but the data about that thing is different in one from the other. So there's all these data anomalies, and one of the things that relational model strives for in particular is erasing those anomalies, making it to where they don't happen. And there's a whole process for this. It's very sophisticated. It's called normalization. We'll go over this later in the semester. I'll have a lecture on it and some examples. I've got those already. I've already made videos on this one. But making sure that things are consistent so you don't have these anomalies happen is one of the key features of relational databases. But the way you do this can slow down the performance. So there's a certain balance between the two that you're always striving for. All right, so the things I'm talking about in this video, again, you can read all this stuff. This is all and more. All this stuff's written out somewhere in your notes and text and slides and etc. I did actually have the slides keyed up to go, and then I didn't actually ever open them. Let's look at the slides real quick. I just want to make sure I haven't forgot anything in chapter 1, and then I'll be going over to chapter 2 right after I've finished this video, because I'm actually didn't realize I'm behind where I wanted to be. So so did we go over these different various types? Those the hierarchical and network and all that stuff. And a little bit about the evolution. You can like read more about that on your own. Just know about this. That's something you kind of want to know the basics of, like the order. Like hierarchical will be first, and then network, and then relational, and then object oriented, and then like some other weird ones we're not really going to go over in detail. We talked about the DBMS just now, database management system. Persistent. Just remember, like in the whole IT world, the term persistent means it's stored hard somewhere. Like if you cut the power, it's still there. That's one way of thinking of it. A persistent thing. It's non-volatile is another word for that. So the data remains until you delete it or update it or whatever. And this is just showing you things that you can store as data. So these slides, I'm not a read the slides kind of person. I know you guys hate that. So and you tune out. You probably tune out At least I'm talking. Here's my thing. I don't like to read scripts in these videos because I've seen videos for students like that, and I fall asleep because the person's reciting something, and at least it sounds like I'm talking to you. You're still probably bored, but I'm hoping that it's a little bit more. It's a little easier to. I know I'm rambling too a little bit, but it's a little easier for me to listen to without getting tired. When I hear somebody just kind of talking, like a YouTube video, which is what this is. All right. So accuracy, validity, and timeliness of data, that sort of relates tangentially to the whole integrity thing that I was talking about. And there's a different concept. I talked a little bit about, single user or multi-user. The enterprise database is like the highest level. When you talk about stuff like how Google, it's basically a database of web hits or whatever, that's past relational. That's like really, it's going to be NoSQL solutions that are really sophisticated that are not what we're going to learn about in this class as much. We're going to focus on relational. But enterprise would be like that company I worked for. That was enterprise because you had several, probably a few dozen project managers who were all looking stuff up on the same database management system, often the same databases, maybe some of the same tables. So you need like an enterprise solution for that, maybe, or somewhere between work group and enterprise. So one other thing I wanted to say about the file cabinets too when it came to data integrity, and this reminds me of see how you have centralized and distributed. You could have a distributed database of file cabinets, right? So if you think about a company has records on employees and they have them in file cabinets as before the computerized day, right? They could have copies of those. They could have the same file cabinet system duplicated in several different locations. So this is, again, where update anomaly would be a problem. You update at one location. Think about old banks and stuff, yeah, I guess that bank is probably the best example. You go to that branch and you update your records there, but they don't update it in the other, especially if they just use paper records. Obviously nobody does anymore, but that's sort of like the historical version of the current version, right? And when I say distributed, it's not exactly the same thing. Technically it is distributed. You just have copies in different places. That's different repositories, different sites. Distributed also is an example of the most common distributed database that you use all the time is, it just went out, DNS, the domain name service. That is a distributed database. So what that means is that you put in a word, a domain name or whatever, and you get back the numerical IP is the result of that query. And the way that's maintained is in a distributed way. And it's updated, distributed. It is hierarchical actually as well, but that's the most common one because DNS is a hierarchical database. But you do have if you make a change to the IP, the domain name points to a different IP that propagates over the distributed network in a procedural way that makes sure that everything's up to date, but also tenable. Like you get the right IP address, numerical address back. It used to be a flat file example. When you talk about database kinds, there's flat file they talk about in there. The original domain name service was a flat file called host.txt. I think the original one was even called that, or host.txt. You can still have it as part of your local DNS client if you want. It'll look at that first, and then it'll go look at the rest of the DNS across the whole internet. But originally it was kind of like, okay, Harvard's 64 and Berkeley is 23 or whatever, what they actually were. And it would be a file that you would send out copies of when things got changed, and you had to keep it up to date manually so that your computers on the very early internet knew where to go. And over time that turned into the DNS, which is an automatic sort of distributed net database of So that was a big tangent, but just to show you there's all kinds of places where databases come up and these different models come up. And of course you got cloud stuff now. If you think about AWS, that's a solutions. You can do IT projects, programming projects on there, but also Oracle has a database solution that's cloud-based now. So you don't actually have to have the physical server on site. You can just subscribe to their service and you can you can spin up a database or even a database management system right in their cloud and then create your databases there, as long as you got the internet access. All right, I think that's enough for you to go on. I just kind of wanted to hit the key points you should be thinking about for chapter 1. And again, I'm going to put this up. For the future semesters, the semester I'm making this for, it's like a 1 day past the first week, and I wanted to make sure that everybody sees this first and then moves on to the chapter 2 material where we talk more about modeling and starting to design and create a database and what you have to think about there. But this is it for chapter 1, and be looking for chapter 2 soon.